In this segment, we'll finish our overview of the RTS, looking at recursion, register storage, and some other details. Let's start by looking at the recursive factorial function here on lines 24 through 33. We assume that you understand the basics of recursion from prior study, by the way. Brush up on that if not. This function is a sort of a classic, and it computes the factorial of its parameter val. So for instance, if val was 4, then 4 times 3 times 2 times 1 is 24 is what it should return. And we do in fact have an example call of factorial 4 down in the main that returns exactly that, as you can see here on line 47, and in the result down here on line 71, factorial 1 is 24, or factorial 4, I'm sorry, is 24. Now, for any val greater than 1, the function does this by calling itself here on line 31 with a smaller number, val minus 1. Let's trace the example call, factorial of 4. Factorial 4 calls factorial on 3. And that calls then in turn factorial on 2, and that calls factorial on 1. And that last call, factorial on 1, would finally stop passing the buck, and it would return 1, since val is 1 in that call, to factorial of 2, and that multiplies the 1 by 2 and returns 2 to factorial of 3 and multiplies in its 3 and returns 6 to factorial of 4, and finally multiplies into 4, returning 24 to main. So we get a chain of factorial calls, each returning their respective value up the chain back to main. Now, it's critical that each call act independently with its own val and its own temp value. In particular, one should not think of a recursive function call as jumping back to the top of the current call like some sort of elaborate loop. That's not what it's doing. Each recursive call begins an entirely different instance of the function. And that's not to say, by the way, that the code itself is duplicated, of course. All instances have the same code, but they have different stack frames. And this is what makes them distinct calls. So let's take a look at our diagram here. And so we start with a stack frame for factorial on 4, and we can see the val of 4 and the temp not yet assigned. And then factorial 4, of course, we'll call 4 factorial 3, thus, and val, of course, 3 there. And then, of course, factorial 3 calls factorial of 2. And factorial of 2 calls factorial of 1. And factorial of 1 finally does not call anybody, but simply returns, leaving the value 1 just above the top of factorial 2's stack frame, per the discussion we had earlier on return values, as you may recall. And that means that factorial 2 computes a value of 2 for temp, multiplying in the value of val. And now, of course, factorial of 2 also returns and leaves that 2 value down on the top of factorial 3's stack frame. And factorial 3 takes that return, of course, multiplies it by its value for 6. And the 6 is what it returns then. And the factorial of 3 frame goes away. And we leave a residue return value of 6 above the frame for factorial of 4, which multiplies that, of course, by 4. I'm sure you get the picture by now, to produce a value of 23. Factorial of 4 return, 24, I'm sorry, factorial of 4 returns, and the returned value of 24 is finally, after all of this Sturm und Drang, what main winds up seeing as the result of its factorial 4 call. The critical picture to gain from this is that recursion generates what we might call a cascade of stack frames, and ultimately that cascade rolls back to the original caller. So here's question 1. It's easy enough to forget the base case, the non-recursive case, when n is less than, or val, I'm sorry, is less than 2 in factorial, for instance, and just do the recursive case. Now, if we dropped the if and got that out of there totally, and just did the recursive call, then the result would be a long, quiet silence while we ran factorial, followed by a runtime fault. What would be happening during the long, quiet silence? Coming back from a pause there, the RTS would be filling up with stack frames, since each factorial call would result in another with progressively lower, even negative val parameters. They'd never stop. The RTS isn't infinite. A typical RTS might be able to hold 1,000,000 frames. It takes a bit of time to fill it up with 1,000,000 frames, at which point you'll get a fault. Okay, so now question 2. In theory, factorial is a well-written recursion. It does have a base case, which I just restored here, and it simply returns an answer without further recursion in that case. Each recursive call reduces the problem size by 1, thus driving toward the base case, so the recursion does eventually stop. But what would happen to the RTS if we called factorial on, say, 10 million? Aside from integer overflow, by the way, which would occur as well. Just thinking about what will happen to the RTS if I call factorial of 10 million. Again, coming back from the pause there, it's pretty straightforward, considering the just mentioned fact that an RTS might allow around 1,000,000 frames before overflowing. Even a correct recursion may still overflow the RTS before it bottoms out. This is important. In academic discussions of recursion, the essential elements of a good recursion are supposed to be, 1, you have to have a base case, and 2, you must have recursive calls that move toward the base case. But an industrial recursion has a third requirement. You must not call too deeply, since the RTS is finite in extent. Okay, so let's move on to a few other concepts related to RTS now that we've done the factorial bit. The argv parameter in main is obviously on the RTS. It's a parameter. But what about the block of pointers to which it points? The block of character pointers. Is that block dynamically allocated on the runtime heap? And question 3, consider the output of line 49, which I have down here, printed out argv, as you can see in the result down at the bottom here. That shows the output. And what does that say about the question I just posed regarding the location of the block of character pointers? Coming back from a pause there, it indicates that the block of pointers itself, the starting address of which is the value of argv, the 2673856, is in the same area of memory as the parameters. It's really pretty close to the location of argv itself. So it's in main's stack frame, somewhere in there. There is the block of pointers, maybe over here in the corner of the stack frame, along with the argv itself. That's fairly typical for command line parameter target data. It's often just jammed into the bottommost stack frame as part of setting up the program. Now, we alluded earlier to other stack frame content aside from the parameters, the locals, and the return value. Any state relevant to a function call may be stored in the call's stack frame. For instance, a function needs to know what point in machine language to return to after it's called. FA might be called, for instance, in our example code, either from line 44 here, or from line 21 in FB up here. When it returns, it's expected to jump back to the point just after the call, to resume execution in the caller. That location is placed in its stack frame by the caller and used when FA returns. In addition to that, any CPU has registers that hold current working data, such as the value of temporary computations or of heavily used variables. When a function is called, the register contents that are currently being used by the caller often must be saved so that the called function can use the CPU registers for its own purposes. The caller's register content goes in the stack frame for the called function to restore upon return. A more complete list, then, of typical stack frame content would include parameters, local variables, the saved register content from the caller, the location to return to when we're done, and then finally a spot for the return value, generally at the bottom of the stack frame. The order will depend on the compiler. Don't count on any particular order, but those contents are typical. Now, for our next topic, let's look a little bit at the amount of time that a function call takes. A function call takes so little source code, perhaps just a fraction of a line even, that it's tempting to think of it as a simple operation. But consider the overhead now required to make the call. Entirely aside from running the function itself, we have adding a new stack frame, adjusting the TOS pointer, copying parameter values into the stack frame, saving registers into the stack frame, copying the return location into the stack frame, and then finally jumping to the function. And then the function runs, and coming back we have saving the return value into the stack frame, restoring the caller's register content, dropping the current stack frame, and reducing the TOS pointer, and then finally jumping back to the return location. Now that's a fair bit of work, so it's reasonable to view a single function call as having overhead similar to several lines of code. Reducing the number of function calls can be essential to code efficiency in certain cases. And finally, let's close by looking at the most common source of security holes in C programs. Consider the example code here repeated from the slide, from the transcript. The example function is aptly named sitting duck, and you can see it doesn't do a whole lot of complex stuff, just reads in the buffer. But what happens if a malicious user doesn't honor that pleading comment and instead enters a much longer string than 9 characters? Assume they might even enter one with non-ASCII values, for instance, so they could induce your code to read arbitrary bytes into memory past the end of buffer. Question 4. What, then, generally speaking, will get trashed? What data lies after the end of buffer? Coming back from a pause there. Well, buffer is a local variable, and so it's sitting in the stack frame for sitting duck. The data after it, further down in memory, might be sitting duck's saved register state, for instance. Other local variables, if there were any. And critically, the return location. Now, if the input is long enough, the overwrite might even reach down, in fact, into lower stack frames. It can go down as far as the user pleases. So that scanf invites a caller to write whatever they like into the current stack frame and the frames below it. A sufficiently clever and malicious user might even write data in the fashion shown here in the diagram, where it contains machine language code, labeled my code, and a value overriding the return location that jumps instead, as the arrow indicates, straight to the introduced machine language code. Now, when sitting duck returns after the scanf, it jumps mindlessly into the code provided by the user, and suddenly your program is running externally provided code. This is a buffer overflow attack, and it remains one of the most common sources of security holes to this date, especially in C code. Generally, that scanf is instead some code that reads information supplied over the internet from another program and sloppily neglects to check whether the data being transmitted exceeds the buffer space provided for it. The lesson is to always check any data provided from outside your program to be sure it doesn't exceed the size of the memory space you're copying it into.